Markov chains. Stochastic matrices and Markov chains. We're going to start by looking at a sample problem, and we're going to continue using this sample problem throughout the rest of this long video split into 3 shorter videos. So the sample problem has to do with 3 competing companies offering satellite television service to a city with 100,000 households. Each year, Company A retains 70% of their customers but loses 20% to Company B and 10% to Company C. I want you to notice that adds up to 100%. Company B keeps 80% of their customers each year but loses 15% to A and 5% to C. And Company C retains 70% of their customers each year but loses 15% to A and 15% to B. This year, Company A has 15,000 subscribers, B has 20,000 subscribers, and C has 65,000 subscribers. The question is, how many subscribers will each company have next year? And how many will that have in 3 years? So of course, if we were just asked the first question, we could do a lot of little side problems to figure this out. But if we want to find out how much in 3 years or 5 years or 10 years or 15 years, we're going to want to use some linear algebra. So let's take a look at how we can begin this problem. The first step in solving a problem like this is to populate P, which is a matrix of transition probabilities. Matrix of transition probabilities, also called stochastic, which means regarding conjecture. So basically what we're looking at is we want to capture the probability that each person will stay with Company A or move from A to B or move from A to C and so forth. We want to do all of this regarding probabilities. I also want to point out that probabilities have to be between 0 and 1 inclusive, 0 where it's certainly not going to happen and 1 where it's 100% going to happen. And that the sum of the column of probabilities has to be 1. So we're going to talk about that as we fill in this stochastic matrix for the problem. So if you'll notice, I've copied over just the part that had to do with probabilities from our sample question. And I'm going to start looking at from A and B and C to A and B and C. So I'm going to start with A. Company A retains 70%. So A keeps 70%, but 20% go to Company B and 10% to Company C. So what I want to see you do is think about A, because this is from A. This has to add to 1. And we're not going to use any negatives. So I'm not going to say loses 20 to Company B, so that's minus 0.2. No way. We're saying they have to add to 1. They have to be probabilities. So A keeps 70%. B gets 20% from A, and C gets 10% from A. Notice that sum is 1. And then I'll move on to B. Company B keeps 80%. So pay attention to what you're doing, because I have a lot of students who try to put 80% right up here at the top. But remember, we're saying B is keeping 80%. So from B to B would be right here in the middle. And then loses 15% to A. So from B to A is 0.15. And 5% to C. Remember, 5 is 0.05. Make sure that you don't write that as 0.5, which is 50%. Again, notice that adds to 1. And then we'll finish up with C. C retains 70%. So from C to C, 15 to Company A, and 15 to Company B. Again, we'll note that that adds to 1. And this is our matrix of transition probabilities, which we are calling P. Before we continue with this sample question, I want to make sure we understand which matrices are stochastic. So take a look at these and then just circle or cross off or do whatever you need to do to determine which of these matrices are stochastic. So I'm going to begin with the first matrix. Right away, I see that I have a negative value, not stochastic. Second matrix, that's the one to the right, I can see that this is not square and therefore not stochastic. Let's look at our third matrix. It looks like the first column adds to 1, the second column adds to 1, and the third column adds to 1. And it is a square matrix, and therefore that is stochastic. So that gets a nice green check mark. Looking at the next one, adds to 1, adds to 1, adds to 1. Therefore, this is stochastic. Next one, how good are you at adding fractions? 1/2, 1/3, and 1/6. Remember, common denominator, this is 3/6, this is 2/6, and 1/6, that gives me 6/6, so those add to 1. 1/4, 1/2, 1/4, that adds to 1. 1/4, 1/3, 1/3, not looking good, but again, make sure you know what you're doing. This would be 3/12. This would be times 4, so 4/12, and this would be times 4, so 4/12, so that's 11/12, so it does not add to 1. So this is another no. And finally, we have our identity matrix, and yes, that is a stochastic matrix. Recall that the question that we're trying to answer is how many subscribers will each company have at the end of 1 year, and how many will each have at the end of 3 years. So what we need is we need to be able to find the nth state matrix of a Markov chain. P is what we have already discovered. That's the probability matrix, probability transition matrix. And x sub 0 is the initial state of the matrix. Now we haven't talked about that. This year, it told us company A has 15,000 subscribers, B has 20,000 subscribers, and C has 65,000 subscribers. That's a total of 100,000 customers. And so we have to then write that as a proportion or a decimal. So 15,000 divided by 100,000 and write that as a decimal. So make sure that you're using, again, a column matrix that adds to 1. So you can see in decimals, I already have both of those values in there. If I want to find the state at the end of 1 year or the next year, I'm going to take p to the n times x sub 0. So for this case, I would just take p and multiply it by x, which is x sub 0. Now, this value, I would then have to take times 100,000. And that would give me the actual value. So if I don't take it times 100,000, that's giving me the proportions or percentages. But if I want to know the raw values, I'm going to take it times 100,000. That's at the first year. So depending on the question asked, this one they said how many subscribers, I would want to take that times 100,000. Now, at the end of 3 years, notice I'm going to not take this value times 3. I'm going to take p to the third power and then times x and then times 100,000. And that's going to get, and of course I would round to the nearest whole person, but that's going to give me the value at the end or at 3 years. I would like you to try a practice, and on this slide we're going to just focus on writing P, the probability transition matrix, and x sub 0, which is the initial state. So if you would, press pause, read over this question. When you're ready, press play to see how you did on that, and then on the next slide we're going to use those matrices to find the number of customers for each theater on day 7. So again, the first thing we have to do is take a look at the fact that we have 3 different options. We have AMC, we have Alamo, and we have people who didn't go to the theater. So of the people who attended AMC night 1, 10% will attend again on night 2, and 5% will go to Alamo, which means anybody else, and that's what's not given in this, if there's 10% going back to AMC and 5% going to Alamo, that's 85% of people aren't going to the movies 2 nights in a row. Of the people who attend Alamo night 1, 8% will attend again, and 6% will attend AMC, so that's only 14%. So again, you have to be doing that math yourself. So we should have come up with this probability matrix, 0.1, 0.05, and 0.85, 0.06, 0.08, and 0.86, and then 0.03, 0.04, and 0.93. The other matrix we should have come up with on this slide is the initial state matrix. And again, we can see that there are a total of 1,000 customers where 300 people attend AMC night 1, 400 attend Alamo, and 3 people don't attend the theater. So that's a total of 1,000 people. So we're going to write that again as a percent of the whole. So 300 divided by 1,000 and so forth. So I popped back over to desmos.com/matrix. I entered in matrix P, matrix X0, which I'm just calling X. And remember, we're looking for day 7. So for day 7, I'm going to take P to the 7th power. I'm sorry, that needs to be a capital P to the 7th power. And then I'm going to multiply that by X. And again, this gives me the proportion of people. It doesn't give me the number of people. So if I want the number of people, I'm going to have to take each of those values times 1,000 because that's how many people we started with. So again, I would have to do some rounding of people here, which always gets interesting, but about 34 people, 42 people, and 924 people for each of those different categories. Steady state of a Markov chain. I'm going to assume that you have been with me through the beginning of this video, but I do plan to, break this into different parts. And so if you've just started with steady state, I want you to take a look at the question that we've been working with from the first part of this video, which has to do with competing satellite television services. So through this, we came up with P, which is the transition matrix, and X, which is the initial value of where everybody is. So we can see, again, where we came up with this. We said A retains 70%, so from A to A is 70, loses 20% to B, so that's 0.2 in the second row, because 0.2 would go from A to B, and 0.1 would go from A to C, and so forth. That's where we got the values for P. And for X sub 0, that says this year, company A has 15,000 subscribers, B has 20,000, and C has 65,000, and that was a total of 100,000 people, and so we divided. So now you're caught up. So from here, what we want to do is we talked about what happens after 1 year, or after 7 years, or after 10 years. So if we want to find out after 5 years, we would take P to the 5th times X. If we wanted to find out after 10 years, we would take P to the 10th times X. And if we wanted to find out for 20 years, P to the 20th, P to the 20th times X. And I can see what's happening is my values are not changing quite as much, right? So what if I did P to the 100th times X? I'm starting to feel like there's very little wiggle room. Or in calculus, we would call that a limit. So that's what we're looking at here, is we can see that this matrix is approaching something called a steady state. In the example that we just looked at, X sub n showed little change as X increased past a certain value. eventually reaching a steady state. And obviously in calculus, that is what we call a limit. Now, it's not important that you understand calculus or understand limits. What we're saying is, as the value of n increases, as the number of times we do something increases, we are going to get closer and closer and closer to what is the steady state of our matrix. Now, that's all well and good, but we need to know when our matrix will have a steady state or not. So we're looking at the stochastic matrices, which are the probability transition matrices, which we call P. I'm using A and B just for clarity because that's what I'm going to use here in Desmos. So if I'm looking at matrix A, right now, A doesn't appear to be regular only because there is a 0. Remember, for a matrix to be regular, all of the entries have to be positive, and 0 is not positive. But if I take A and square it, I can see that now I have all positive entries, and therefore A would be a regular stochastic matrix. Looking at B, I've got a real problem with all the zeros. So if I take B and square it, notice I get a whole column of zeros. What if I take B to the 14th power? Yep, a whole column of zeros. What if I would take B to the 100th power? Yep, a whole column of zeros. So therefore, B is not a regular stochastic matrix. We're getting closer to being able to find a steady state matrix. There are 3 steps. The first is to check that the matrix of transition probabilities P is a regular matrix. And in this case, this is P. We're going back to that example we've already been working with. And I can see that I already have all positive entries. So I don't have to worry about checking it because when I'm multiplying this, I'm going to continue to get all positive entries. So step 1 is done. Step 2 is the hardest part because for step 3, I'm going to allow you to use technology to compute. So for step 2, it says write the system of linear equations obtained from the matrix equation Px equals x. So what we're saying is this is Px equals x. I want to write an equation from that and that the sum of the probabilities of x1, x2, and x3 has to equal 1 to write a system of equations. So here's how this is going to look. This first equation says 0.7x1 plus 0.15x2 plus 0.15 x3 is equal to x1. So I'm going to rewrite that so that it's equal to 0. So this equation now becomes 0.7, no, just kidding. This equation, after I subtract 1x1 from each side, becomes negative 0.3x1 plus 0.15x2 plus 0.15x3 equals 0. Now I'm going to do the same thing for the next row. So I'm going to get rid of all that so we have room to work. 0.2x1 plus 0.8x2 plus 0.15x3, again coming just from the second row, is equal to x2. I'm going to subtract x2 from each side. And on the right side, I'm going to get 0. And on the left side, I'm going to get 0.2x1. And then I have 0.8 minus 1, so that's minus 0.2x2. And then plus 0.15x3 is equal to 0. And I'm going to do that one more time with my final row. So now I'm looking at the third row and saying 0.10x1 plus 0.05x2 plus 0.7x3 is equal to x3. And again, that's 1x3, so I'm going to subtract 1x3 from each side. And on the right side, that gives me 0. On the left side, I have 0.1 x1 plus 0.05 x2. I have 0.7 and minus 1, so that's minus 0.3 x3 and equals 0. And then my final equation is 1x1 plus 1x2 plus 1x3 is equal to 1. This is my new system of equations. What we want to do now is to solve the system of equations. So in order to solve, you can see what I've done is I've taken that system of equations that we came up with together. Now this is a system of 4 equations with 3 variables. So putting that into a matrix form, I know that when I row reduce this, I'm going to have a row of zeros, and that's okay because I only want 3 solutions, right? I want one for x1, x2, and x3. Now, from here, it just says solve the system. You can solve it however you want. You can solve this system, substitution, elimination, whatever, because you're not going to be required, at least for my class, to show work for this part of it, because obviously you have to show work for where this came from. I would suggest to you that you just use RREF and A, and you can see that that does all of the hard work for me. And I can even convert that to fraction form. So my matrix, my solution is 1/3, 10/21, 4/21. So I'm going to call that matrix X. It's really X bar, but you get the idea. I'm going to make a new matrix, and it's 1/3. And I'm going to type in 1/3, 10/21, whoa, 1/3, 10/21, and 4/21. Now, the other part of this, so it says solve the system, but also then check that if you take P times X bar, you also get X bar. So I have taken P, which was our original P matrix. I just went ahead and re-entered it in here. So if I take P times X, I want you to notice that if I click the fraction button, I do in fact get 1/3, 10/21, and 4/21, verifying that this X matrix is our solid state matrix. I did want to provide you one practice. So again, if you're joining me from the first part of this video, you've already seen this question, and together we came up with P and with X sub 0. So the probability transition matrix and the initial state. I want for you to press pause and come up with the system of equations that we would use. So remember, when we're solving P X bar equals X bar, come up with the system that we would use to solve that equation. When you're ready, press play to see how you did. So I know there were a lot of steps that we kind of went through, but just to recall, we're saying that P times x1, x2, x3 is equal to x1, x2, x3. So this doesn't matter at all. In fact, we're going to forget about that, and we're just going to rewrite these as equations. So this is 0.1x plus x1, 0.06x2 plus 0.03x3 is equal to x1, which means if I subtract x1 from each side, this is now going to be negative 0.9x1, and this is going to be 0. The next one, 0.05x1 plus 0.08x2 plus 0.04x3 is equal to x2. And again, if I subtract x2 from each side, I'm going to get 0. And this is 0.08 minus 1, which is negative 0.92x2. And then for my third equation, 0.85x1 plus 0.86x2 plus plus 0.93x3 is equal to x3. And again, that's 1x3. So subtracting 1x3 from each side, I get 0. And here I get 0.93 minus 1, which is negative 0.07x3. And the final equation is that x1 plus x2 plus x3 is equal to 1. This is the system of equations that I need to solve. Now that we've done the hard work, we just put that system of equations into a matrix, and we're going to let Desmos do the work for us. So we're going to reduced row echelon form of A. That's going to give us our matrix. Again, we can write those as fractions, and then you can certainly check it as well. X is equal to, and then I'm going to make a 3 by 1 matrix. I'm going to put in 4 119ths, 5 119ths, and 110 119ths. And if I take P times X, I should get that same solution. I didn't put P in ahead of time. I'll leave that part for you to do on your own. But this would be our solid state matrix. Absorbing Markov chains. Before we talk about absorbing Markov chains, we want to understand what an absorbing state is. So a state in a Markov chain is called an absorbing state if once the state is entered, it's impossible to leave. That means there has to be a 100% probability that once you're in one state, you'll stay in that state. So thinking about our Markov chains as we did before, and we said this was from A, B, and C, and this was 2. I think we labeled it on the other side before, but that's the same. If I look at A, if I'm coming from A, there is a 100% chance that I'm going to go from A to A, or in other words, I'm going to stay in A. Therefore, A is an absorbing state. Once I'm in A, I can't go anywhere else, kind of like a black hole. For B, if I start in B, there's a 30% chance that I go to B and a 70% chance that I go to C. Again, just looking at this column. So B is not. Same thing for C. If I'm looking at C, there's a 20% chance that I'll go to A, a 40% chance that I'll go to B, and a 40% chance that I'll go to C. So C is not an absorbing state. Now, doing the same thing here from ABC to ABC, notice we have a lot of 1s, but that doesn't necessarily mean that you're going to have an absorbing state. So for instance, from A, there's a 100% chance that I'm going to go to C. That's not an absorbing state because I'm going to go from A to another state. So from state A to state C. So A is not. Now let's look at B. From B, there's a 100% chance that I'll go to B. Therefore, B is an absorbing state. Once you get to B, you don't go anywhere else. If I'm starting from C, there's a 100% chance that I'm going to go to A. Therefore, I'm not staying in C, so C is not an absorbing state. Just as we did with our regular Markov chains, we want to talk about a limiting state or a steady state matrix. And in order for an absorbing Markov chain to have a steady state matrix or a limiting matrix, the following conditions must be met. First of all, of course, the Markov chain has to have at least one absorbing state. So we've already determined that for both of our examples. They each have one absorbing state. For the first one, that's A to A. And for the second one, that was B to B. The second condition is that it's possible for a member of the population to move from any non-absorbing state to an absorbing state in a finite number of transitions. So let's take a look at our first example. Is it possible for any other member of the population to move to A? So remember, this is from, this is to. Now this is my absorbing state. Can any other element move to my absorbing state? Well, sure, they're going to move from C into A. Now, does that mean that B can't? No, B can move to C, and then from C, they can move to A. So this is a transition matrix that would have a limiting matrix. But if I look at my second example, I can see that while I do have an absorbing state in B, if I start in A, I'm 100% of the time going to go to C. And if I start in C, I'm 100% of the time going to go to A. So what's going to happen is all of the non-absorbing states, they're just going to flip-flop or ping-pong back and forth between A and C. Nothing is ever going to go to B because B has zeros as the other entries in that row. Now, before we continue, let's just point out that in order for our matrix to have an absorbing state, you're going to have a 1 along that diagonal. Those are going to be absorbing states. So in each of our examples, that's exactly what has happened. To point out, that is, if you are labeling correctly here, ABC, ABC. So you'll find that the process for finding a steady state matrix, even when we're talking about an absorbing state, is really the same as what we did before. So instead of checking to see that it's a regular transition matrix, we're looking to see that it meets those conditions, that P has an absorbing state, and it feels like it does, and that it's possible to get from B to B, and again, it does. So that is me checking that this is an okay matrix for me to use. And then we're going to do just like we did before. We're going to say 0.4x is equal to x1. So 0.4x1 is equal to x1. 1x2 plus 0.5x3 is equal to x2, and 0.6x1 plus 0.5x3 is equal to x3. So again, where did that come from? In case you didn't join us from our last video, we used the P matrix, the transition probability matrix, just as it was. We took it times x and set it equal to x. And that's where we got those. So again, 0.4x1, 0x2, 0x3 is equal to x1. That was that first equation. I did that for all three equations, and I'm also going to use this equation. And what I'm going to do now is I'm going to write it so that it's in standard form, so that all of the variables are on one side. So for my first equation, I'm simply going to subtract x1, 1x1 from each side. And that gives me negative 0.6 x1 is equal to 0. For my second equation, I'm going to subtract 1x2 from each side. And what happens here is the x2 actually goes away. So I end up with 0.5x3 is equal to 0. Same thing for my third equation. I'm going to subtract x3 from each side, and that gives me 0.6x1 And then I've got minus 0.5x3 is equal to 0. And then I've got x1 plus x2 plus x3 is equal to 1. So this is my new system of equations. And then we're just going to solve that system. So you can choose the method that you wish to solve that system. I'm going to just put them all in a matrix and row reduce it using a calculator. Just as we did for regular Markov chains, now we're just going to use the capabilities of desmos.com/matrix to reduce this matrix for us. So we have the system of equations on the screen. We have the corresponding matrix that has all of our equations. And now I'm just going to let Desmos do its thing. So I'm going to row reduce. And I can see, just as I expected, my last row is going to be zeros. I've got 1x1 is equal to 0, 1x2 is equal to 1, and 1x3 is equal to 0. So my final solution for x bar, and I'm just going to call it x here, is going to be a 3 by 1 matrix, and it's going to be 0, 1, 0. That is the steady state matrix for this particular question. And notice that it does line up with the fact that B, which was the absorbing state, is eventually going to absorb everything. We have just one practice left to finish up this video. So this is similar to the last question. Obviously, we have 4 variables for equations. And the solution here is going to be a little bit different, but I would like you to get just as far as you can on your own before you press play. So go ahead and press pause and try the question now. All right, step 1, check to see that the matrix of transition probabilities has an absorbing state and members can move from a non-absorbing state to an absorbing state. So again, that means I'm looking across that diagonal and I see that I've got an absorbing state here from B to B and one here from D to D. So I definitely have that one checked. Now, can I get into B? Sure. Can I get into D? Sure. So yes, I can. So I can continue with this, and now we're going to write the system of linear equations obtained from Px equals x, and remember that x is just x1, x2, x3, x4. This is the matrix we're trying to solve for, that x bar, that is the limiting matrix or the steady state matrix. And then, of course, it's just equals to that again. So each line is going to result in an equation. For instance, my first line is 0.5x1, 0x2, so 0.2x3, 0x4 is equal to x1. My next line, 0.2x1 plus 1x2 plus 0.3x3 is equal to x2. Next line, we have 0.1x1, and again, I'm just looking right here. 0.1x1 plus 0.4x3 is equal to x3. And then we have the final one, 0.2x1 plus 0.1x3 is equal to x4. And then we have, if I get rid of all of my mess, we have that final equation that says x1 plus x2 plus x3 plus x4 is equal to 1. So what I have now is I'm going to have a matrix, and this equation I'm going to subtract x1 from each side, and that gives me 0.5x1 minus 1x1 gives me negative 0.5x1. So that gives me negative 0.5x1, 0x2, 0.2x3, 0x4 is equal to 0. The next line, I'm going to subtract x2 from each side. In this case, it cancels out completely. So that gives me 0.2x1, 0x2, 0.3x3, 0x4 is equal to 0. Now I'm going to subtract x3 from each side. That's going to give me negative 0.6 instead. So I have 0.1x1, 0x2, negative 0.6x3, 0x4 is equal to 0. And then finally subtracting x4 from each side, I get, oh, I'm sorry, I'm going to go back and fix that. This should have been plus x4 is equal to x4. And then now I'm going to subtract x4 from each side. And that gives me 0.2x1, 0x2, 0.1x3, 0x4 is equal to 0. And then, of course, my last one is 1, 1, 1, 1, 1, and that's from this equation. So that is the matrix equation that, or matrix that I am going to row reduce to find the solution. Now that we have our matrix that includes all 4 of our equations along with our final equation that x1 plus x2 plus x3 plus x4 is equal to 1, I'm going to go ahead and row reduce that. So RREF, A, and we can see that I get a solution. And that solution says that 1x1 is equal to 0, 1x2 plus 1x4 is equal to 1, 1x3 is equal to 0, and now I have 2 rows. So this is the first time that I have 2 rows of zeros. And we know that we expected this last row to be 0 because we only have 4 variables. But the fact that I have 2 rows of zeros tells me that I'm going to have more than one solution to this particular system. We have a free variable. So let's talk about how we can handle that. When we row reduced our matrix, this is the matrix that we came up with. And again, this tells me that x1 is equal to 0. Again, this is an augmented matrix. So x1 is equal to 0. x2 plus x4 is equal to 1. x3 is equal to 0. x4 is free. So just as we did before, we're just going to use, we're going to give the solution parametrically. We're going to say let x4 be equal to t. So my solution, my x bar, is going to have 0 for x1. For x2, let's rewrite that. So x2 plus, I'm going to replace x4 with t is equal to 1. So x2 is going to be 1 minus t. So that goes here. x3 was 0, and x4 we're letting be t. So this is my solution to the system. Now I do want to point out in your textbook, just to save space, they write it like this: 0, 1 minus t, 0, t, transpose. This is the correct way that I would like you to do it. They're doing this in your textbook just because it doesn't take up as much space up and down. Coming up next is section 2.6, which is all about applications of matrix operations.